Similar situation for parallel plates. Oh, only at the ends. Well, I typically will not bother with the ends, but if you want to know, it's a similar story. So, John, if you don't want to be bothered. All right. You try to squeeze that out of me. You know, what am I not going to ask you? No, it's the same principle. It might come in handy some other time. You never know. I mean, maybe not the capacitor plate. But what we have here in a capacitor is a very similar idea. Let's just go back to basics. We charge up the plate with pluses and minuses by attaching it to a battery. And charges will flow over because pluses try to get away from each other, and they run over as far as they can. Minuses will run this way, say. And again, we have our pluses producing a field, which will go to minus. And in the center of something like this, again, by symmetry, there's no particular reason why it should bow out that way or bow out that way. You're right in the dead middle. Of course, as you get toward the edge, as I say, the lines will tend to bow out. I'm exaggerating perhaps a little bit here, but they will tend to avoid each other if they can. You get near the edge, you get this bowing effect, which we call fringing field. Well, I should make it symmetric. And you get something like that. And it all comes out of the basic principles. The electric field, by definition, goes from plus to minus. And we use a little symmetry to say that right in the dead middle, there's probably only one place, one line that's really perfectly straight. In the very dead middle of this thing. But then everything else kind of bows out a little bit, but we can usually neglect the bowing until we get pretty close to the edge. Sure. Basic principles in operation. Any other? Oh, and again, we're using some principles here that if you have a flat plate, that the infinite sheet has lines going vertically forever, if it's infinite. Again, because there's no reason to go left or right, forward or back, go straight up. And if there's no other place for the lines to go, if there's no other negative charge someplace to catch them, in principle, they go on forever. So you just have this giant array of lines coming out of an infinite sheet going on forever until they reach some negative charge someplace else in the universe. So we're just about ready to officially start. That was just fun and games. What we have, I put up here one of our diagrams of the way the course is structured, and we have those topics for today's exam. We have the electric charge, its basic quantity, gives rise, in the case of electrostatics, we dealt with Coulomb's law, which is the basic law of what a point charge will do. It turns out that you can, that'll give you the charge effect of one point charge. And by adding up all the point charges you have, like we just did for the dipole, the fields due to all the point charges, you can get a combined field. You can also get what's called continuous distributions, where you don't break it down into point by point by point, but kind of a smear of charge, right? We call that a continuous distribution. Some people confuse it. One person asked me, does that mean, is that different from uniform? What does uniform mean compared to continuous? They made a little thing in mind. Continuous just means that there's no break. It's the opposite of discontinuous. Right? So continuous just means that it's smoothly varying. But it doesn't have to be constant. It doesn't have to be uniform. In principle, I could have a sheet of charge, which was continuous. Means I can describe it as being continuous, but it doesn't have to be uniform. There could be a crack here. So that is not exactly uniform. There's a crack, but it's continuous. For example, it could. We try to avoid complicated situations. But so typically, I'll say I have a continuous sheet of charge, and usually I'll say it's uniform as well. Or it might not be. Right? But, so there is a difference. Okay. And then, so we have the Coulomb way of adding up all the point charges and their effects. Or we have the Gauss law, where you can find the field in some global way for certain. You can actually solve some problems specifically, like simple ones, points, lines, spheres. Pretty much, you can have shells, you can have solid spheres, you could have spheres within spheres, things like that. Simple, symmetrical cases to find electric fields, the forces and fields. And then we also have potential energies, and then we just moved on to electric circuits, including resistors and capacitors. So that's the general outline. I hope you sort of see the overall picture and a concept of each of them. So what we can do today, I'd like to just respond to your problems at this point. 3 hours before the exam, it's a little late, but maybe we can straighten out a few things here. So what I would do, frankly, is take questions, if you have some up front. I'll try to organize them so that we can go through them in an orderly way, not running back and forth if possible. And we'll just go from there, we'll just wing it. So do you have any particular questions? That look means you either know everything or you know nothing. There's always that question, so lost that I can't even ask a question. That's happened to me a lot. Yes, sir. Yeah, okay. Question is the different dielectric, para-electric, and ferro-electric. That's an interesting subject. I hope you others are interested. Any other topics? Yes, sir. Okay. The question is, like if I have, say it again for me. Yeah? Yeah. From here? To go where? Up? Yeah, okay. Thank you. Did I do that to you? Oh, that's, all right, electron is moving parallel. Oh, okay, it's moving parallel to the x-axis. Huh? No, that's okay. We have somebody who's prepared here. So, okay, well, okay, we can do this one. All right, we'll do that. Any other? Yep, get us started. If you think of something. Yes, ma'am. Uh-huh. Okay. Okay, that is actually similar but different from this one, right? I mean, this is, okay, that's the one. The question was, what's this? Do you remember it in detail? Shoot an electron, yeah. Particularly a charged ring, right, okay. What velocity? What velocity do I start it out in order to make it stop, as I recall? Okay. All right. Now those are a couple of good things. Okay. Any other thoughts? These two are somewhat similar. You can see where we have a charged something and a moving something. So those are generically similar. Yes, ma'am? About which circuits? RC. Okay. How much we should know? Yeah, I'll talk about that. Okay, fair enough. All right. Well, that should keep us busy. Well, let's take care of this dielectric thing. The dielectric, paraelectric, and ferroelectric. Very simply thing. The dielectric refers to the fact that if you put any material in an electric field, because the material contains electric charges, they will respond to the external electric field by doing what we call polarizing. Meaning that there will be separation of the positive and negative charges. Now, the degree to which it does that is the degree to which these positive and negative charges can really move. If you have an insulator, by definition, the charges are pretty much stuck on their atoms and molecules. So an insulator like this tabletop, the electrons can't really move in this material. They're stuck on the atoms in plastic of this tabletop. I think it's plastic. Okay. So what you see, the problem the electron has in a case like this, it's in an atom with a positive nucleus, which it really likes that positive nucleus. It's positive and it's nearby. So there's a strong attraction to hold that electron onto the atom in an insulator. And when we put on an electric field, that electric field is competing with the electric field that's holding the electron onto the atom. And typically the fields that we can apply out from the outside are relatively small. If we put the field on large enough, we can actually tear the electron out from the atom, and that will break the material down. It will, that's known as electrical breakdown. You can actually do it. In a big enough field, you will leave behind the positive and you will tear the electron down. And that's sort of what happens when we have a spark in the air. We put on such a big field that we actually tear the electrons off the oxygen, and we're pulling them off, pulling the nucleus the other way. We can actually tear them apart and get this electrical discharge through the air. You can do that, the extreme large fields. Typically, we just separate them in small distances in the case of an insulator. So you get the feeling for that. On the other hand, for a conductor, which is the case we had of the electrostatic doorbell, if you put that in an electric field, the electrons can move rather freely. So if I put a plus charge here, the electrons, even on the other side of the little ball here, can run over here, leaving behind their pluses, and you get an attraction. And that's why the electrostatic doorbell, remember that with the big plates and the little bell, bang back and forth? That would move rather gingerly when I put it on the field. If you put an insulating ball here, the separation of charge is not that great, the attraction is not so great. So, but this is polarization of the material. It started out electrically neutral, and it gets polarized. So that happens to everything simply because everything contains electric charges. Yes, sir? Yeah, that's the mechanism why it goes bong, bong, bong. But when it gets to here, there are positive charges here produced by that old big Van de Graaff. Or I don't know, maybe I don't know whether Van de Graaff produces a negative or positive. Let's say let me change it around. Let me make a Van de Graaff negative. So what's going to happen is that's negative. It's going to make this side positive. It's going to repel the negative charges that way. Okay. So the ball comes over, and it's got all these negative charges over here. They want to get away from each other like nobody's business. So this comes over. Some of the charges jump onto the ball. At which point the ball is negative, and it wants to run away from this guy. So he swings over, and over here we give them a pass to get off. So the electric charge that's jumped on here can now jump off here. Everything's happy, but he's moving, so he bounces off the wall. He comes back. He hits the wall again, gets some more charges, repelled, goes back into the bong, bong, bong. So that's how that works. It doesn't work nearly so well with an insulating ball because the attraction here is not nearly as strong. Sometimes you can just get it. Insulating ball will just come over and stick. Can't even pick up any charge because the first charge that gets on repels the next guy trying to get on because this charge can't get out of the way. He's stuck. He's insulated. So that kind of thing happens. Yes, that's why the electrostatic doorbell works that way. Okay, I don't want to spend too much time on this, but the point is that this kind of thing. It's property of all materials. Okay, the paraelectric is the case where the material has its own structural dipoles due to the structure. Now, our famous example is water, H2O. Here's O. I'm going to put two hydrogens on there. Where should I put them? Where do they go? Well, oxygen, we know from chemistry, attracts electrons. Hydrogen was willing to give up a little electron, so there's electropositivity, electronegativity. Some charge was going to come off the hydrogen, some electrons are going to go off, and this guy's going to attract them. So this guy's going to become a little positive, and this will be a little negative. Now, if I were the next hydrogen getting on here, I see this positive hydrogen over here. If I were a hydrogen, I would get as far away as possible, right, from the other hydrogen, because they repel each other. So if you sat right here, they'd repel. That wouldn't be a happy place at all. So this would be the ideal situation if I were making water, and all I was worried about is the repulsion of these things. But it turns out, somebody explained to me in chemistry something called lone pairs or something. I remember the word now. Lone pairs. Somehow over here there's some structural thing due to the electronic structure which doesn't allow that hydrogen to sit there. It pushes it away, off center. So that hydrogen goes up here, which means that there's more plus charge up here than there is, and minus charge down here. You have a net dipole, which we call this way. So due to structure, some few things, in fact common things like water, have built-in dipoles due to their nature. And you can't get rid of that dipole unless you break the molecule. It's just there. Somebody asked me a question like, well, suppose is it moving? Does it lose its dipole if it's moving? No. And I think I put the answer, suppose this was a baseball bat. If it's a baseball bat, it has a kind of shape and a structure. And the only way you can change it is by breaking the baseball bat. It can tumble. In thermal motion, the molecules can tumble. So on the average, there's no dipole moment. That's thermal motion will make the water molecules tumble. And on the average, what he's pointing up is down. But it's built into the structure. The only way you get rid of it is by breaking the structure. So if you have a water fluid, you'll have these dipoles pointing every which way thermally. What happens, though, if you put them in an electric field, then in an external electric field, like I tried to do over here, well, let me put it in the same direction here as I did before. If I put a big electric field here, what's going to happen is that the plus end of the molecule is going to want to turn along the field, and the minus end is want to go that way, it will turn. And so the molecule will prefer to be along the field. But the dipole moment will tend to want to be along the electric field that you apply. Basic principles again, right? Pluses move upfield, minuses move downfield. That's simple. But the thing is that everybody just doesn't go there and sit. Problem is it's thermal motion due to the heat. And so things will move around. And in fact, you'll have just a slight, well, depends on how strong the field is and what the temperature is, but you'll have a difference between the population along the field and opposite of the field, with a tendency to be along the field. Slightly more, at least slightly more, will point along the field. This is a very common thing in statistics, that there's a preference to be along the field because the field is turning the molecules this way, but the thermal motion says to be random. Okay? So that's your paramagnetic case. And what happens is you have a bigger dipole, because these are big dipoles. You see, this, you're moving the charge, say, from one end of an atom to another. That's a tiny, tiny thing. Here, I have a dipole which is a whole atom's worth, or molecule's worth of dipole. So the dipole polarization here is much larger, usually in the case of paramagnets, because they have a built-in dipole, and they just move. Well, the other difference is that in this one, what you're doing is moving electrons, so the electrons move rather fast. And so in this case, you can speak about a torque R cross the force. You can speak about a force because the molecule has its own dipole, and when you put it in a field, that whole dipole tries to orient. Here it's different. The field is creating the dipole. So if the field moves, the dipole goes right with it, because it's an electron that's moving fast. So there's a difference in time scale between these two, I think I talked about. And the third case, the ferroelectric, is just that you have certain materials where, again for structural reasons, what can happen is that there'll be some kind of a structure where the electric center of gravity, is where the electric superposition of the pluses and minuses results in a net dipole within the crystal. Something like this. And where this might be a little off-center, something like that, so it's really not quite balanced plus and minuses. And in that case, you have a whole crystal which has a net dipole moment. And that is a big dipole moment. So, and that could potentially be very slow to move, because you have to move, not only just tilt a molecule, you have to maybe move an atom if you want to switch the direction of polarization in an electric field. So that's the general idea of the three kinds of materials, yes. And for future use, we will have similar cases for the magnetic thing, where you have something where we have dimagnets, where everything gets a little magnetic when you put another magnet near it. We'll have paramagnets, where we'll have permanent magnets which are loosely sticking around, and they align a little bit in field. And we will have, of course, ferromagnets, where you have internal magnetization or internal structure all lined up of magnets. Okay, so hope that's good enough for you. It's RC, yeah, well, the thing that all I really cared for you to know is that if you have a circuit with a resistance and a capacitance, the charging and discharging of it, yes, ma'am. Yes, of course. Yeah, that's what somebody asked about that. Oh, yeah, okay, yeah, okay, yeah, okay. So you want the graphs of this situation too? Okay, graphs and how you get bus. Okay, we better move along then. The RC is something like this. Again, leaving out the details of the mathematical description of the growth of charge and current and so on. What happens is, if you start out with a circuit like this, with a battery, a resistor, and a capacitor, and you close the circuit here. Okay, the battery wants to send out, say, plus charge through the resistor. Now, the capacitor has a voltage on it, which is equal to, I always have to start out with C equals Q over V, the basic. So the voltage is equal to Q over C. So if we were to plot the voltage on the capacitor as a function of time, when you first close the switch, the question is, the only way there's a voltage on this capacitor is if there's charge on it. And at first, there's no charge. Right? Before you start out with no charge. I close the switch, current starts to flow. Current being the amount of charge that passes per unit time. So current starts to flow, starts to build up on this thing. So it starts out first with no voltage on it because there's no charge. So in fact, this could be a plot of the charge on the capacitor, because that's what's giving it the voltage. Right? So it could be the charge on the capacitor or the voltage on the capacitor. So the voltage starts out at 0. So we can have, likewise, the voltage on the resistor. Now, the current is flowing through the resistor. And the current in the resistor is equal to the current times R, the resistor. So at the beginning, the voltage is, see, there's no voltage on this, so it all must